Integrating quantum emitters into on-chip photonic circuits is crucial for realizing integrated quantum photonics, with potential applications in quantum information processing. Hexagonal boron nitride, hBN, is an attractive material for this purpose, offering a high refractive index, low losses in the visible range, and favorable fabrication techniques. Its properties, including atomically flat surfaces and a wide bandgap, make it suitable for photonics applications. hBN also hosts optically active point defects that act as excellent single-photon emitters, SPES, in various wavelength ranges. However, these emitters occur randomly in the flake, hindering scalable integration in photonic devices. The recent demonstration of local generation of blue-emitting color centers using a focused electron beam has offered an attractive workaround. This E-beam technique allows for high control of the emitter position and average number, and consistently exhibits a reproducible emission wavelength, predominant in-plane polarization, short lifetime, and high optical coherence. The authors leverage this E-beam technique in a completely top-down approach for fabricating an elementary quantum photonic device, where emitter generation is included as an additional step in the fabrication process. They fabricate short waveguides with semicircular grating couplers and subsequently embed quantum emitters in the waveguide by local irradiation. Photoluminescence characterization demonstrates the coupling of both the excitation laser and the SPE emission into the waveguide. The authors choose a ridge waveguide geometry, which is simple to realize, where light is confined by refractive index contrast between hBN and the environment. For a point dipole emitting at 440 nanometers with an in-plane polarization orthogonal to the waveguide main axis and located at the mode antinode, 23% of the light is coupled to the waveguide in each direction, of which 18% is extracted towards the top direction to be collected by a Na equals 0.8 lens. The fabrication process involves exfoliating high-pressure, high-temperature grown hBN on a silicon oxide (C) substrate, selecting single crystals using atomic force microscopy and cathodoluminescence, and fabricating the waveguide using electron beam lithography and reactive ion etching. The design of a hexagonal boron nitride (hBN) waveguide embedding quantum emitters is presented. The waveguide is fabricated from hBN crystals through a series of steps. Electron beam lithography with a Wraith-Alene system at 20 kV is used to pattern the waveguide shape. A 30 nanometers layer of aluminum is then deposited as a mask for the subsequent etching process. The etching process, performed using fluoride reactive ion etching, results in an etching speed of 33 nanometers per minute. The aluminum mask is then dissolved in a co-solution. Single photon emitters, SPES, are generated in the fabricated waveguide by inserting the sample into a scanning electron microscope and irradiating precise positions using a static focused beam. The irradiation parameters yield an average SPE yield of order 1 per irradiated site, although the generation process remains partially probabilistic. The fabricated waveguide is characterized in a confocal microscope at room temperature, demonstrating its capability to couple light in, transmit it, and couple it out. The waveguide transmission spectrum is inferred from the ratio between the transmitted and reflected spectra of a broadband laser, exhibiting etaloning due to Fabry-Perot oscillations. Notably, the B-center zerophonon line at 440 nanometers coincides with a maximum of transmission. Photoluminescence measurements are performed on the emitters, excited with a 405 nanometers laser diode in pulsed regime. Two waveguides, denoted WG1 and WG2, with thicknesses of 60 nanometers and 220 nanometers, respectively, are fabricated. WG1 is generated with a lower dose, resulting in a single SPE with favorable characteristics, while WG2 is generated with a higher dose, resulting in a localized ensemble of SPES. The fabrication process of the hBN waveguide is illustrated, including exfoliation, E-beam lithography, aluminum deposition, etching, and irradiation. A scanning electron microscope image of the final structure demonstrates the successful fabrication of the waveguide. The waveguide characterization results are presented, including the waveguide under laser illumination and the waveguide transmission spectrum. Spectroscopy measurements on waveguide WG2 utilize a laser with an 80 MHz repetition rate in 400 microwatts power, operating within the linear regime of the emitter. Photoluminescence signals are filtered and collected using either a charge-coupled device camera or avalanche photodiodes. Two detection path configurations are compared, exciting from the top. Configuration 1 involves exciting and detecting via the same free space mode, yielding the ensemble spectrum with a 440 nanometers zero-phonon line and phonon sidebands. Configuration 2 involves exciting from the top and detecting from a grating coupler, as depicted in Figure 4b, resulting in an essentially unchanged spectrum, indicating coupling to the guided mode. Individual emitter characterization compares three configurations. Configurations 1 and 2 involve exciting directly above the emitter, with corresponding CCD images displaying single photon emission at the excitation spot and output ports, demonstrating coupling to the guided mode and free space via grating couplers. This coupling is enabled by the large angle between the waveguide axis and the SPE polarization axis. Emitter lifetime is measured at 1.83 nanoseconds, consistent with prior measurements of B centers in non-processed flakes. Hanbury-Brown and Twist setup measurements of the autocorrelation function G2 yield 0.35 plus or minus 0.04 in configuration 1, indicating predominantly single B center origin. Switching to configuration 2 results in a count rate about 4 times lower, indicating 45% lower emitter waveguide coupling than ideal simulations. Data presented in Figures 4 and 5 illustrate spectroscopy measurements and individual emitter characterization. Figure 5 presents the experimental results for 3 configurations of excitation and collection port, showcasing the device's capability for guided single photon emission at room temperature. The figure displays CCD images of the device photoluminescence in configurations 1 and 2, indicating the laser position and collection spot with violet and blue arrows, respectively. The polarization of the emitter with respect to the waveguide direction is also shown, with the orange arrow denoting the waveguide axis and the blue line the dipole axis. The G2 measurements for configurations 1, 2, and 3 are presented, exhibiting antibunching with G2, 0, values of 0.33 plus or minus 0.06, 0.33 plus or minus 0.06, and 0.26 plus or minus 0.04, respectively. These results demonstrate that the G2 is not degraded through propagation in the structure, and that the excitation laser can be coupled to the guided mode to excite the single photon emitter. The coincidence histograms show the period difference and coincidences, indicating the presence of single photons. Although the lower count rate may be attributed to deviations of the grating coupler dimensions from the nominal values, the results demonstrate the feasibility of combining fabrication and B-center generation in a complete process starting from hBN exfoliation, yielding deterministic emitter positioning and guided single photons at room temperature. Future improvements will require optimized photonic structures and emitter-to-photonic mode coupling, as well as a more controlled single photon emitter generation process. Please provide the transcript that needs to be refined, and I'll transform it into a concise, technically accurate summary suitable for voiceover narration, following the guidelines you provided.